We are happy to have Mohammed Abouzaid from Colombia today, and he will speak about Morava case theory and Arnol'd conjecture.
Thank you very much. Thanks, Jan, for the invitation. So I'm going to talk about some work that I did with Andrew Blumberg. We've been doing this work for about 4 years. And finally, the paper has been released. It's on the archive as of a few weeks ago. So this result is going to be, it's a result about symplectic topology. But at the end, I kind of left some few slides open. I didn't write anything on them. And I'm hoping maybe to just give some speculation about what this probably tells us about mirror symmetry. So the way I will do this is that I'll give the statement of the result, and in the statement of the result, there's going to be no Morava K theory, no fancy algebraic topology. Then I will introduce what these Morava K theories are and kind of how they appear and how they're useful, and then I'll give some technical discussion about what's involved in using the Morava K theories in symplectic topology. And then, as I said, my hope is that given, especially depending on the interest, given the interests of some of the audience, I may be very brief about part 3 and instead say what I can say about mirror symmetry in this context. Okay, so so this is already a problem, so I'm going to just do this to take care of it. So what is the statement that we prove? So the statement that we prove is a classical version of a classical conjecture of Arnol'd. It says that you should consider a compact symplectic manifold. This is our compact symplectic manifold. It's called M, and you take a Hamiltonian diffeomorphism. Okay. And a Hamiltonian diffeomorphism is just a symplectomorphism, a diffeomorphism that preserves the symplectic form, but it has some additional condition, which essentially, there's no condition of, which is, essentially saying that it's isotopic to the identity, except that if in the case where H1 is non-zero, you have to also, impose some additional constraint. But let's just imagine a symplectomorphism isotopic to the identity. And so the conjecture of Arnol'd, old conjecture of Arnol'd, says that if you take such a diffeomorphism, then the number of fixed points must be larger than the minimal number of critical points of a function on your function on your manifold. And that one is very difficult to prove, and there's some partial results. But so instead, people often consider the case where you assume that the points, that all the fixed points are non-degenerate. Okay, and here non-degeneracy is basically a version of, like being a Morse. Like non-degeneracy for a diffeomorphism is a little bit like being a Morse function. And then the statement is that the number of fixed points should be larger than the minimal number of critical points of a Morse function. And the number of critical points of a Morse function is something that it's been studied and for a long time, and you can use Morse theory to study it, and we know how to bound it using the homology. Basically, if M is simply connected and of dimension greater than 5, then this number, the minimal number of critical points of a Morse function, is easily extractable from the homology with integral coefficients. Okay, it's basically the minimal number, the minimal rank of a free abelian group, of a complex of free abelian groups whose homology computes the homology of your manifold. That's the bound. So it's completely straightforward to write down. So now it would be great if we could prove that, but we don't quite prove that. We prove something weaker. We prove something at a prime. So if you give yourself a prime number, P, then we prove that the number of fixed points is larger than the rank of the cohomology with FP coefficients. Okay. And if you try to compare this rank, this estimate with the estimate that you get from integral homology, what you see is roughly that you lose some information whenever there are different degrees of cohomology. There are different degrees of cohomology which have torsions of different amounts. So our estimate is not, you can take the maximum over this over all P, and you're not going to get as good an estimate as the integral one. Precisely because there could be, Like in some degree there could be some 3 torsion, in other degree there could be some 5 torsion, and we can't quite detect that. But anyway, but this is our result. So to put it in some context, I should state what was known before, okay? Which is basically that if you make your coefficients have characteristic 0, which means which work over the rationals, this has been known for about 20 years, a little bit more than 20 years. It's due to Fukaya Ono, and it's also separately due to Liu Tian. But what I can say is that the way they proved this is that they took Fleur's old result, who proved this with Z2 coefficients under some very stringent assumptions on M. You basically assume that M, the moduli space of holomorphic spheres on M, can be controlled very well. So we say that symplectic manifold is monotone. So under that assumption, Fleur proved it. But with integral coefficients, again, you have to be a little bit careful with how you make your statement. But outside this context, we don't know. I mean, the result basically is not known. And the best we can do in full generality is characteristic 0 statement, which is again, due to Fukai Ono and Liu Tian. And so this result says we can work in characteristic P. Are there any questions before I move on? I'm very happy to take questions.
Theoretically, it's Floer complex of the graph, of the graph of phi and the diagonal.
Right.
Yeah.
Right. So one perspective on this computation is that it is actually defined. What we're computing is that if you take phi, which is a map from M to M, switch pens, then you can take the graph of phi. Let me just call it M phi, and that lives inside N times M. I mean, if we're a little more precise in M, so you have to do something with symplectic forms. This is Lagrangian. So if you are happy with Lagrangian Floer theory or Fukai categories, you say you're basically computing the Floer homology between the diagonal and this M phi. But really, in some sense, what you are really doing is computing the Lagrangian Floer homology of the diagonal. Because the diagonal and M phi, they're Hamiltonian isotopic, and in Fukai categories, that means that they're equivalent. So you're trying to understand what is the rank of this Floer homology group. And the issue is the Fukai category is only defined over Q, or in characteristic 0 for general M, because the counts of curves only make sense in that setting. But we're going to see that somehow there's a way around this, and this is why at the end of the talk, I'll maybe give some time. I'll give some speculation about what this might say about mirror symmetry.
Can I think of the graph as a deformation of the diagonal? So the Floer homology or the cohomologies are the same as the diagonal? Absolutely.
So the point is that, so you take the diagonal, the Floer homology of the diagonal, you could naively think of it as you take ordinary cohomology and you deform it. But now the question is, how much do you deform it? If you deform it a lot, rank is going to go down. Okay. But the issue is, could you have made sense of this deformation outside of characteristic 0? Okay, that's the problem.
Excuse me, Hamiltonian diffeomorphism is the same as symplectomorphism, or it's a different thing?
It's the same as symplectomorphism is M if M is simply connected, or if H1 of M is 0. Otherwise, it's a little bit like this. It's like the difference between a function and a closed one form. Okay. You can associate to a general symplectomorphism isotopic to the identity a closed one form, and you want that one form to be exact. And if that's the case, then it's Hamiltonian.
Mm-hmm. Okay.
Great. So, as I also write here, this is weaker than what we can prove in this semi-positive case. And the semi-positive case is basically the most general case where Fleur's classical methods apply. Okay, so if I hadn't given you the title of the talk, then what you would imagine that this talk would be about F counts of holomorphic curves with FP coefficients, because that would be the obvious way that you would try to do this. And what I'm saying is that that's not what we do, because I don't know how to do it. I mean, actually, I conjecture that you can do it, but that's another story. We can that's even more speculative than what I plan to say. So instead, what I want to say, I know that this can't see here. Instead, what I want to explain is that the statement uses, oops, there's some accident there, uses something which you should think of as a generalized homology version of Floer theory. Okay, so Floer theory you can think of as you take ordinary cohomology and you deform it. And now what we're going to do is we're going to take a generalized cohomology theory, and the generalized cohomology theory goes under the name Morava K theory. Okay, and so the point is that this Morava K theory it's usually written as K of n. And what's happening here is that there is a prime P that is implicit. Okay, at the beginning I said we're going to prove something about FP coefficients, and there's a prime P and it's implicit, and we're just not going to mention it again. And then there's another number, and this number is the height. Okay, this number is called the height. And if you know a little bit of arithmetic geometry, this is the height in the sense of height of
formal group.
Yeah, sorry, height of formal group. Sorry, word was escaping me.
What is the formal group for Morava K theory?
So the short answer is, in characteristic P, there is a distinguished, the formula will appear in just a second, a distinguished formal group of height n for every n. It's the thing that corresponds to the fact that, x plus y to the p equals x to the p plus y to the p. Yeah. Okay, in characteristic P. So this statement gives rise to okay, and then it's so basically this is why these theories only make sense in characteristic P. But anyway, so right now we're just going to take this as some kind of, what am I trying to say? I'm trying to say there is this black box which we introduce in this paper, which we call Fluir Hamiltonian. Instead of saying Hamiltonian Fluir homology, it's Hamiltonian Fluir K theory, but it's a specific type of K theory. It's Hamiltonian Fluir Morava K theory. Okay, and it's a group. Okay, and this group it has two properties, which is how the application is derived. The first property is that this group, which is associated to Hamiltonian diffeomorphism, to this phi, it admits the ordinary homology, the generalized homology of M with coefficients in Morava K theory. Those are the generalized K theory of the Morava K theory of M. M is your symplectic manifold as a summand. Okay, so that means its rank is bigger than the rank of the ordinary homology. And really, the statement here is just out of pure laziness. Okay, because this should be an isomorphism. So really, you should imagine, we didn't prove it, but we should imagine that this Hamiltonian Fluir homology group is in fact isomorphic to ordinary cohomology, which is why, going back to the question whether we should think of this thing as some deformation of cohomology, yes, it is a deformation, but it's a deformation that doesn't change the underlying vector space or the underlying, spectrum in this, the underlying spectrum. It only changes the multiplicative structure. And this is something we're familiar with because when we look at quantum cohomology, for example, quantum cohomology is a deformation of ordinary cohomology, but it just deforms the product. You don't introduce a new differential. Okay? And that's what we're saying. You do the same thing. You can do the same thing with this Morava K theory world, whatever it is. And things will not be deformed, except we didn't prove that. Instead, we proved that, the usual thing sits as a summand of the old thing. Okay, so this is the first property. And the second property is that, you can compute a rank. And the rank is, for technical reasons, you have to compute the rank over some kind of Novikov field. It's not too surprising. But this rank is smaller than the number of fixed points. Okay. And once you have these two facts, then you can derive the application just from the existence of these groups. So these are the kind of essential facts if you want to use the theory to have an application. Okay, so what I want to say describe next is a little bit more about kind of how one goes from what does it mean that you're working with Morava K theory, but also how does one go from having this statement to the application, because the theorem that I stated does not have the word Morava K theory in it. It just has the word FP coefficients. Okay? And this is some feature of classical algebraic topology, which we're going to use. Okay, so that's next. So first we need to introduce what these people are. So
You had coefficients with Z-mod 2 coefficients before, right? That was the original thing Floer did.
Floer did it with Z-mod 2 coefficients under the assumption that it was monotone, which is basically means that C1 and omega are proportional.
Oh, I see.
And as soon as you move away from that situation, all we have is characteristic zero.
And is the reason for that because some moduli space is a stack or is
Yes.
no stack? Okay.
Yes. And it's actually, if you think about it, and then I don't know if I'll have time to elaborate on this. It's not because it's a stack, it's because it's a derived stack.
Oh.
And which in my world means because it's not because you have an orbifold, it's because you have an orbifold with a vector bundle on it, and you're supposed to describe your moduli space as a zero locus of a section. Okay, so you can think of this as some kind of derived stack, and the behavior, that's actually, the integrality is worse for when you introduce this orbi bundle over a stack than we're just looking at the naked stack by itself.
I see. So you're saying whatever fix you need is worse than just like ambidexterity, something that.
No, we will use ambidexterity, but you need ambidexterity, and you need to know that ambidexterity is compatible with orientations. So it's somehow, you need ambidexterity not just for orbifolds, but for some kind of derived orbifold. And it turns out not to be so bad.
Thank you.
No problem. Okay, so yes, for those who don't know, ambidexterity is something that may or may not show up to. I think I probably will barely mention it in the end of this talk. Okay, so what is Moravocate theory? So it is a cohomology theory, which I want to insist that it is of non-geometric nature. Okay, so somehow, what does this mean? It doesn't mean something precise, but what it means is like, if you ask me to describe for you generalized cohomology theory, my preference would be to describe Buddhism. Okay, this is something which is completely geometric. You can just explain. You look at manifolds with boundary. You look at manifolds, and then you look at cobordisms between manifolds, and look at maps from manifolds to spaces up to cobordism, and that creates a cohomology theory. And if you're a slightly different nature, you can think, we're going to talk about vector bundles, complex vector bundles, stable complex vector bundles up to stable isomorphism. Okay? And that is, again, something of geometric nature. Moravocate theory is not like that. Okay, it's constructed from complex cobordism by doing a bunch of algebra. Okay, so that's what I mean by it's of non-geometric nature, and it's really serious. It's not, it's not like, well, if things were, if we just don't understand its geometric nature, and if we understood better, we'd be able to do it. There are some real indications in its, it's kind of, we know there's an obstruction to make it commutative. And usually anything that's sufficiently nice and geometric is very nice and commutative. And you take the product of x and y, and you can understand exactly what happens. And here, there are some kind of deep obstructions that arise. So anyway, that's the first thing that you say. So we have to treat it as a piece of algebra, unfortunately. So as I said before, it depends on two parameters, a prime number and a height. And maybe the most important thing for us is that when you look at its coefficients, and the coefficients of a generalized cohomology theory just means the value at a point. Okay, a generalized cohomology theory is something that assigns to spaces groups, graded groups, and well, in particular, it assigns something to the point, which is the simplest space you could possibly imagine. And what we want to assign to it is some kind of Laurent polynomials over Fp. And these Laurent polynomials, the variable in the Laurent polynomial has a non-trivial degree, and that degree is what I wrote over here, 2 times p to the n minus 1. Okay. Now, the essential feature that will allow us to extract the theorem about Fp from this kind of fancy Morava nonsense is that, this degree, this quantity that I wrote over here, 2 times p to the n minus 1, it goes to infinity as n goes to infinity, which means that you have these degrees that are further and further, the kind of the correction to this just being Fp is living in further and further away from 0. Okay? And so that means if you study this on any space, which is finite on any finite space, like not something complicated like Cp infinity, but rather something simple like Cpn, then you will see, again, I'm sorry, I will try to fix this glitch. You will see that the ranks, that you have some kind of rank inequality of this nature, which is that for any n, the rank of Morava-K theory is less than or equal to the rank of cohomology with FP coefficients. This follows from the Atiyah-Herzberg spectral sequence. And but when n is large enough, then all the differentials in the Atiyah-Herzberg spectral sequence have to vanish, basically because the pieces are too far away for there to be a non-trivial differential. And in that case, you get equality. So the proof, really what we prove, is that the Morava-K theory, the rank of the Morava-K theory of M is a bound on the number of fixed points. And then we conclude that's true for every height. And therefore, we conclude it for FP by taking the limit as n goes to infinity. And this is, of course, the stupidest kind of, the most elementary type of limit you can take. The subject of algebraic topology is full of complicated ways in which you could try to start with information with these Morava-K theories for height n and assemble them together and to get information about FP. But here we're doing something kind of very, very naive. We're just saying, let's just take the ranks, which are just numbers, and observe that these ranks stabilize and obtain from that the result.
Excuse me, I want to get a feeling of this Morava-K theory, that given the space, what you get is the algebra, which is over this Morava phenomenon.
So precisely what you,
right?
so if you give me a space, you get a module over this ring, over this Laurent polynomial ring. Laurent polynomial ring. It's in fact a little bit tricky, and I spent quite a bit of time trying to understand. It turns out that at the prime 2, this Morava-K theory is really badly not commutative, even at the level of homotopy groups, but level of homotopy, I shouldn't say that, even at the homotopy category. But it turns out that you still get a module over this. So that statement is always correct. What is going to happen is that things that we are used to, like, the cup product, the existence of a cup product, which is an algebra, which the fact that the cohomology of a space is an algebra over the underlying ring, that is not true for these theories. So this is what happens. Like, just you take a module, this is a module over a non-commutative ring. It becomes very difficult to do algebra kind of, again, with cohomology.
It's the Kn,
Kn is not commutative.
It's not a commutative ring.
It's not a commutative ring, no. Again, it's not a commutative ring in the sense of the homotopy theorists. Now, its homotopy groups are commutative. So it's really quite a strange object, which is partly why I say it's of non-geometric nature. You're doing some kind of strange algebra. Okay. Any more questions, please? We have people. Okay. So let me say more about Morava-K theories. So I want to state some key properties. So the first one is, I've already said that it's obtained as a quotient, through many steps, but ultimately obtained as a quotient of complex cobordism. So there is this map. Okay, so we will use this, gets used later, but right now what that means, if you take any cohomology theory which has a map from complex cobordism, then what that means is that you have Tom isomorphism theorems for complex vector bundles, which means that you take a complex vector bundle, you take cohomology, you twist it by the you take a complex vector bundle with space, you take cohomology twisted by that complex vector bundle, and that is isomorphic to the cohomology of the space you started with, up to some shift having to do with the degree. Okay, so you can actually characterize Morava-K theory by, in fact, describing the first Chern class, because in this context, where if you have complex orientation, then you can make sense of Chern class. You can describe the first Chern class of the line bundle over CP infinity, okay, which is O of P. Okay. The line bundle of degree P over CP infinity, that's a complex vector bundle. It has a Chern class. And, well, the Chern class in this theory is quite interesting. It is given by Vn minus 1. Remember, Kn, sorry, I'm just going to write again, so that we know what we're talking about. Kn, the coefficients, this is this Fp with Vn plus or minus. Okay, so this Vn and this Vn are the same. So the variable in Kn shows up times U to the P to the N, where U is the generator of the cohomology. So basically U lies in degree 2 of the cohomology of CP infinity. And it's the same U that you are used to when you do ordinary cohomology, basically. It's the same U. Now, clearly, this formula does not look anything like the formula that usually shows up when you do Chern class of this line bundle O of P on CP infinity with respect to the usual theory. And the reason is that the formal group law that's associated to the usual ordinary cohomology is the additive group law, and the formal group law that is associated to Morovocating theory is this formal group law of height n, which I've just basically written a formula for. I mean, I didn't say it precisely, but you can derive from this the formal group law. Okay, so if you have this formula for the first Chern class,
in this case, the n you call the height, right?
Sorry, can you repeat again?
And it's the n that you use.
N is the height. N is the height. N is the height. Yeah, and then you can see that this is a degree 2 element basically by checking the degree of U is 2, and then I told you what the degree of the n, and it should add up correctly if I did it correctly. Okay, so this first Chern class, well, what it allows you to do, if you have if you know the first Chern class of the line bundle, then you have the Giesing sequence, which tells you, look at the circle bundle associated to the line bundle and try to compute the cohomology of the circle bundle. And the Giesing sequence tells you that basically the cup product, okay, the cup product with the Chern class, the kernel and the co-kernel, gives you a long exact sequence where the middle term in the exact sequence is the cohomology of the total space of the circle. That's the Giesing sequence. In this case, cupping with this class is injective, but the most important thing is that the co-kernel, if you take the cohomology of CP infinity and you mod out by Vn minus 1 times U to the Pn, well, that's the same thing as modding out by U to the Pn. So you've basically killed everything in the cohomology of CP infinity, which has degree bigger than n, bigger than P to the n. So that means it has finite rank. Okay? So again, this is the shocking thing about this theory. You start with CP infinity. Its cohomology is basically power series, but let's just say free polynomial algebra in one variable, okay? Variable U of degree 2. Let's ignore completions. Okay, then you pass from from space with infinite cohomology to the circle bundle, unit circle bundle over it, which is basically this length space, infinite length space if you're a topologist. And now the cohomology of this infinite length space is finite dimensional. Okay. And this is the heart of why Morava K theories are useful. Okay, this length space, you can think of it abstractly, if you like to think abstractly, as the classifying space for the cyclic group of order P. I wanted to switch colors. Classifying space of the cyclic group of order P. And usually, what are we used to? We're used to kind of compute. You take a finite group, and you compute the cohomology of your space with coefficient, you're classifying space for this finite group cohomology. And you know that if you work with characteristic 0, then there is no cohomology, okay? Because you can average, everything disappears. Okay? If you work with FP coefficients, it's really complicated. I mean, this cohomology of BCP, it's not so complicated. There's a generator in degree 1 and a generator in degree 2, and they have some nice relation. But the generator in degree 2, all of the powers are non-zero. It looks like the cohomology of CP infinity, basically, because all the powers of the degree 2 generators are non-trivial. Okay, but in this theory, something magical happens, and all that stuff that's very complicated disappears, and you end up with a finite rank with finite rank. Okay, and this fact, it's extremely easy once you know this fact to go from this to show that any finite group, the classifying space of any finite group has finite cohomology. Because you go through some induction, you go to Lorayser spectral sequence and the structure of finite groups and CELO subgroups and things like that. It's not very hard. But it is, people, you may have, in fact, Arnol'd said some words about ambidexterity, and people think of it as some kind of magical property. It's nothing, it's just this fact. And from this, you can derive everything else. So anyway, but of course,
the finite dimensional finite rank, that's over Kn.
Over Kn, yes.
Yeah,
the cohomology of the classifying space, okay, over Kn is finite dimensional. And I wrote, and there is a fundamental class. And what I mean by there is a fundamental class is, in degree 0 is that the homology is also finite dimensional. Okay, that's not very hard. And then there is an element which, again, I'm just to be perverse, I will call it like the fundamental class of BCP. And it lives in the homology and it lives in degree 0. Okay, so that if I apply the cap product, which is how cohomology acts on homology, I get an isomorphism. I get an isomorphism between, so that now I'm running out of room, but so cap with the fundamental class, BCP, gives an iso from cohomology to homology. Okay, just like with manifolds. Okay, so again, the way you want to think about it is from the point of view of Morava K-theory, BCP is a manifold. Okay, finite groups, classifying spaces, finite groups are manifold. And this is kind of the essential input. Once you have this, you need to kind of assemble this. You go from the cyclic group to finite groups. Okay, and that I'm not going to say much about. But really, what very good. Just again, sorry, just to clear off the what Greenleaf and Sadowski proved. This is in the mid-90s. Is that if you take any finite group, okay, then then there is a fundamental class then the classifying space of the finite group has a fundamental class in Morava K-theory, which basically means there is a natural isomorphism here, which is given by cap. So now, what we want to do, yes,
it's isomorphic. The homology is isomorphic to something which I cannot read.
Are we on this side?
Yeah.
Homology.
All right, good. Okay.
Right. So the cohomology is isomorphic to the homology.
Okay, good.
And this is an isomorphism that preserves degrees. Okay. In the manifold case, the homology is isomorphic to the cohomology with a shift. And that shift is the dimension. Okay. But in this case, in Morava K-theory, all classifying spaces of finite groups are manifolds of dimension 0. Okay. And because of that, well, you get this isomorphism. Again, they behave like manifolds of dimensions. Okay, so now what I want to say is that this input, which again, it's basically algebra. It's some input. You start with this Morava K-theory. Somebody has to tell you that it exists and that it has this this Chern class, the line bundle of degree p over CP infinity has this Chern class. And once somebody's done that, and it's, who's done that? Well, basically Morava did it. But if you really wanted to understand how it's done, then I think Mironov is really the person kind of with the clearest explanation of what's happening. But anyway, once they've done it, you can just keep pushing the crank and just computing. You get this computation. Now we're doing Fluir theory. We're not going to encounter classifying spaces of finite groups like that. What's going to happen instead is that we are going to encounter some moduli spaces of holomorphic curves. And those moduli spaces of holomorphic curves are going to have isotropy. So they're going to be basically stacks. And what we want to do is we want to assemble the statement that, that algebra tells us, this ambidexterity statement, which tells us that somehow if you, in the stacky direction, things are okay, and we have this manifold result. We have this kind of isomorphism. We have this ambidexterity result with the actual space direction, where there's an actual manifold. This is what I mean by combining it with Poincaré duality. And the easiest way to combine it is to assume that you have what is called global charts. So I'm going to just assume that I have X, okay, and this is going to be a compact, almost complex orbifold. Okay. So you can have can have your favorite definition of this. I'm going to just assume that I have some manifold M, okay, which is complex manifold, and I have a group G, okay, and let's just assume for simplicity that it's finite, and X is obtained as the quotient of M by G. Okay, it's not the greatest definition, but okay. So now in this case, what do you do? Well, M the dimension of the manifold is n. So if you were working upstairs before taking the quotient, you expect that the cohomology and the homology are isomorphic. Okay, so now we want to work downstairs, but we can't work with the quotient. Okay, because the quotient can have some singularities, and the singularities will introduce some spurious terms, and we don't want that. Instead, we work with the Borel construction. Okay, so what's the Borel construction? The Borel construction, I mean, I think it's familiar to people. So the Borel construction is you take your manifold, you cross it with a free space with a G action, and then you mod out by G. So the point of the Borel construction is that it maps down to X with fibers given by these classifying spaces. Okay, so let me write that here. With fiber B gamma. And so in particular, what you can now, sorry, doesn't map to X, it maps to M. No, I'm giving myself, sorry. No, it maps to X.
It's an M fiber bundle over, oh, sorry.
Yeah, there's two ways of thinking about it. Yeah, you can also describe it as an M fiber. Maybe the easiest way for me to do is what you said. Yes, indeed. So maybe that's, I will adopt that as a simpler thing to do. It lives over M over B gamma, BG, that's what they called it. And this is X, and the fiber is M. This is one BX, yeah, and this is G. Okay, so in this way, what you can do is you can combine Poincare duality in the fiber, which is M, and this ambidexterity statement in the base, which is G, to derive the statement of Poincare duality in the total space, which is this Borel construction. Okay, and then this statement again, it's it's not. I mean, by itself, just proving this is not that difficult. As I said, it's basically some kind of spectral sequence. What is more difficult is to prove then that this is kind of a meaningful notion. That is, if you took orbifold and you presented it as M mod G in two different ways, okay, that you would get the same isomorphism, and that's been done. Okay, so this is our input. So how are we going to use this? Okay, well, to use this, what we need is some idea for how to define Fluir homology with coefficients, not in ordinary homology, but in generalized homology theory. Okay, so let's do the simplest case. Okay, and here I said, let's say that we have a pair of Hamiltonian orbits, because I'm thinking again about my general situation of my kind of actual application of this symplectomorphism. But you can also say, let's imagine that you have some kind of Morse function somewhere. Okay. And it has two critical points. And the critical points are called P and Q. And now, these two.
Excuse me, what is VFC?
Virtual, thank you. VFC stands for virtual fundamental chain.
Okay, thank you.
Yeah, well, class, yeah, but the problem is that we're doing chain level stories. So working with a class is not quite enough. We have to work at the chain level. So I'm going to say virtual fundamental chains. Okay. And indeed, this first example, it's enough to just have the class, the homology class. But once you go beyond this first example, it will become basically necessary to really work at the chain level. And this is the problem here, which is that you can't work at the chain level when you're doing generalized homology theory. It means you have to work with spectra. That's life. Okay, so anyway, so we have this P and this Q, and there is some moduli space. Okay, and the moduli space, I denote M bar PQ, and it's the space of flow lines between them. Okay. Space of flow lines between them. So I illustrated it as like these two flow lines. Okay, so if I have like a standard Morse function on the circle, and there is a min and a max, there's a flow line that goes this way and a flow line that goes this way. So this M bar is 2 points. Okay. But in general, it could be a much more complicated manifold or space. But let's assume that it's regular. Okay. And for it to be regular, basically means it is a manifold. And not just a manifold, it's kind of it's a manifold, and it's transversely cut out. It's somehow, it achieves, if you were to perturb it, it would only change by cobordism. That's basically what it means. So we want, in this context, using this data to construct, to define the kind of the Fluir homology, okay, of this setup, of this Morse function, but not with ordinary cohomology. With ordinary cohomology, we would just count. We would say, well, if it's zero dimensional, I see how many elements it has, and I introduce a differential, which is the number of elements counted with signs. But now the manifold may not be zero dimensional, but it should still contribute if you're working with a generalized cohomology. And the way you do this is that, well, you need some assumptions. And the point is that in Fluir theory, one of the outcomes of Fluir theory is that these moduli spaces that we get, they're not just manifolds. They're not just smooth manifolds. They're, in fact, they have almost complex structures. Okay? They have almost complex structures, which means they define an element of complex Buddhism. Okay? They define an element of complex Buddhism. And I don't want to say that I could just say that, but a better way to say this is that they actually have a fundamental class. They have a fundamental class in complex Buddhism. So if you want to see what this means in practice, what it means is that the Buddhism, I use this, and again, this is not what people do. You can talk about Buddhism homology and Buddhism cohomology. There's an upper star and a lower star. Okay, and what is Buddhism homology? Buddhism homology is almost complex manifolds mapping to your target. Okay? And what is Buddhism cohomology? Buddhism cohomology is manifolds with an almost complex structure in the normal bundle mapping to your target. So again, assume the target is a manifold. You take your manifold, it maps to your domain. It maps to the target. You assume that both of them are manifolds. Then you look at the normal bundle or the stable normal bundle, and you give yourself an almost complex structure on the normal bundle. And the point is that it's easy to see geometrically that Buddhism, the cohomology version of Buddhism is a ring, because you can take transverse fiber products. You take one manifold mapping into here, manifold into here. You take the fiber product. If you think a little bit about orientation, you realize in order for this fiber product to have some kind of orientation, what I should assume is that the two maps have orientations along the normal bundle, and together will add up to an orientation along the normal bundle of my fiber product. That's how you make it into a ring. That's why this is cohomology. On the other hand, homology is, well, just maps into the manifold. So now the claim is that if you take an almost complex manifold, it has a fundamental class, which means that these two things are isomorphic. Okay? But what is the isomorphism? The isomorphism is you observe that the manifold itself is almost complex, and therefore it defines a Buddhism class, like the map by the identity. And so then you take anything mapping, any almost complex manifold, any manifold with an orientation of the normal bundle mapping to M, and you use the orientation of M to turn that into an orientation of into an almost complex structure on the manifold itself. So that's the isomorphism between cohomology and homology, and something extremely geometric. Now, what we can take this geometric thing and say that what we're going to do is we're going to build some kind of Fluir complex. But with coefficients in a complex Buddhism. And how we're going to do it? We're going to take this ring, which is the complex cobordism of a point. So that's what I'm drawing here, complex cobordism of a point, mu. And now there's this element, and therefore we can take a two-term complex.
Do you actually want the ring, or do you want a complex of spectra?
It doesn't. In this case, it doesn't matter. The next step won't make sense. Okay, yeah, because again, I want, at the end, the only thing we use is the existence of the homology theory. So ideally, we'd be able to just describe the homologies and not talk about spectra. Why would we need to talk about spectra? So here, you can do it. You can just say, there is this two-term complex of groups. There is an element. You take the kernel and the co-kernel, basically take the cone, and then you just compute the homology. That's good enough. But as Arnol'd was saying, this is going to be a problem. This is going to be a problem if we have more than 2 orbits. It only works for 2 orbits. Okay. So what we have to do in general is we have to work at the level of spectra. And I'm not going to say what spectra are, but really the right thing to do, and I think it's okay because I've been talking already for 45 minutes. So what you should imagine is, just like when you do ordinary homological algebra, some constructions you cannot do at the level of homology. And instead, you have to work with chain complexes. This is exactly the same phenomenon. Okay, so let me give an example. So the example is very simply that let's assume that we have 3 orbits, P, Q, and R. Okay. And so now the space of things between the moduli space between P and Q, this is fine. This is a closed manifold. And the moduli space between Q and R is also a closed manifold. So these are objects of the the elements of Buddhism ring. Okay, but there is one more piece of information, which is that the moduli space of things that go from P to R, that is not a closed manifold. It is a manifold with boundary, and its boundary is given by the product of MPQ and MQR. So the way that you should think about it is that MPQ and MQR, they give you maps of chain complexes, and you can compose them, and the composition is given represented by the products of manifolds. And now the data that you have is a null homotopy for this composition. And it's clear that this is not something you would have been able to do at the level of just homology, to formulate at the level of homology groups if you were dealing with chain complexes. Now, it's true that if you had it, and if you tried to compute, then you could extract a spectral sequence, and in that spectral sequence, this would be a term in one of the pages of the differential. Okay? But you cannot define something by constructing a spectral. Nobody ever constructs a spectral sequence by hand. All the pages, this doesn't exist. What you do is you need to construct the thing whose filtration is, gives rise to the pages of the spectral sequence, and the thing usually is a chain complex, but in this context, unfortunately, it's a spectrum. Okay, so how should you think about this? You should think about this that, instead, when we did 2 terms, we just take some kind of cone. Okay, there's just something here, and then you attach something, and you just take some kind of cone. Okay, when you take a 3-term complex, when you take 3 of them, you have to do this iteratively. You first attach a cone, then there is like even more. You attach R. You have to add another cell. Okay, and the point is that the cell is being attached non-trivially to the cone part. If you know some like language of infinity categories, especially as it's used in symplectic topology, this is very, very similar to a twisted complex. Okay, it's not, you don't just have maps between successive terms. You also have these arrows that go all the way around, and the equations that they satisfy is exactly this blue equation. Okay, exactly this blue equation. Okay, sorry. Okay, so now there's a problem. And there's a problem, which is that the story is very nice, and we could have used it, and it would be great if we could use it to define Fluir theoretic complex Buddhism, but we cannot. And the reason we cannot is because the moduli spaces may not be regular, which means they may not be manifolds. And at first, what you think is what Arnol'd said is that, well, they're not manifold because of this isotropy stuff, but that's not really the problem. I mean, that problem is we can handle. It's because they're more. It's more than that. So let me say what's needed. So what we need instead is like what Fluir theory gives you is not a complex manifold, but what you should call a complex-oriented Kurenishi chart, Kurenishi space. Okay, so I am not going to define this. Or I will give an idea of how to define this in just 1 minute. But let's now just take this as a given, some notion, which if you're maybe a homotopy theorist, you want to think of like derived or befold, complex-oriented derived or befold. It's a relatively safe thing to think. But but it's in some generalization of the notion of manifold. And what we prove, is that if you with Blumberg, the key technical result is that if you give me a topological space, okay, Z, and let's assume it's compact and Hausdorff, okay, then what you can ask yourself is, can I take this topological space and can I make it? Can I lift it to give it a Kuranishi structure? Okay, and what we prove is that if you can give it an oriented Kuranishi structure with boundary, okay, then you obtain a map. You obtain a map from the cohomology of Z of your space, rel boundary, okay? And I'm going to kind of make the rel boundary even more, highlight it even more, to Morava K theory. And you should think of this as a fundamental class because, ideally we would construct this. We would construct this as a class in the homology of Z with respect to Kn. Okay, but you see, if Z is a nasty topological space, then this is not a great group to study. Just imagine that Z, for example, could be this space. So this space has a cohomology class of degree 1. I think people know what I mean by this space. Cohomology class of degree 1, pseudo-circle, maybe. No, this is not the pseudo-circle. This is just the Warsaw circle. And so anyway, it has a cohomology class of degree 1, but if you compute homology, then it doesn't have homology of degree 1. In the usual sense of homology, you have to use more sophisticated notions, which there's no point in doing. So up to some question of duality, this part here is basically saying we can construct for any Kuranishi space, a virtual fundamental class, rel boundary, and then you have to prove more. You have to prove that you can take this class if you restrict it to the boundary that is compatible with the boundary homomorphism, and you have to prove that if you take a product of two of them, then the multiplication is compatible. Then the choice of the relative fundamental classes is compatible. And if you have all of this, consistently built, then you can kind of run the machine, the Fluir theoretic machine, and try to extract some numbers. So I want to say two things. First thing I want to say is, what should you imagine when I say complex-oriented Kuranishi space? Okay, and when we wrote that part of the paper, many years, 2 or 3 years ago, the only approach we had is a local to global approach. So we had something where we say, the idea is that you have X, which is, let's now just say complex manifold, almost complex. And you have V, which is again an almost complex vector bundle. It can be stable, but it's stably almost complex. But let's just simplify. And you have a group G acting. Okay, and you have one more piece of information because you want to say you have a Kuranishi structure on a space, space Z, and you should imagine it's like some kind of thickening. So you have also a section, which is G equivariant, such that S inverse of 0 mod G is isomorphic to Z. So this is what I mean. This is the simplest way of trying to think about what it means for a Kuranishi space to be for Z to have to come from a Kuranishi space. And what we had to do in the paper is that at the time we didn't know how to do this globally. Instead, we did it locally. We said, well, okay, you have Z, you have some charts. For each chart, you have this thing, you have this presentation, and then you have some overlaps. Okay, and people, if you know the subject, this is very, very annoying and technical part of the subject, and there's lots of trickery. And so we wanted to make sure that we were not, doing any trickery. Okay, so one thing we did is we kind of, we formalized it as much as possible. Okay, so what we do really is we define a category. Let me call it chart of Kuranishi charts. They're of this nature. And we prove that it's monoidal, but it's okay. And then we define what we want to be a functor, a diagram in the category chart. So some kind of, some functor from some poset, let's say, let's call that curly X. Okay. We define a Kurnishi space, we call it a Kurnishi presentation, so that we don't have to, so that there's no name conflict between the different approaches. We define a category chart, and we define a category of diagrams in charts, and that is the category of Kurnishi presentations that we construct. Now, since it's been many years, now there is probably within not too long going to be approaches which show how that in Fluir theory and Gromov-Witten theory we can just construct global charts. That is, we can just you name your moduli space and you fix a genus and energy and boundary conditions and whatever, and then we can produce for you a single manifold with a single group action and a single vector bundle and a single section whose zero locus, once you take the quotient by the group, is your moduli space. So that somehow will simplify quite a few of the technicalities. So anyway, so if you try to read the paper, my suggestion is focus on the global ideas. Don't focus on the local to global patching, because that's probably going to be antiquated and not too long. Okay, so I said I would give some remarks, say some remarks about mirror symmetry, and I think I have like 3 minutes left. So I'm going to say it very quickly. So my main comment, yes.
You can go over the time if you like.
Okay, I'll go a little bit over the time. So my main comment that I want to say is, one, we could have done this. We didn't do this. We could have done this with what the homotopy theorists called KU, which is complex K theory. Okay. So I started by saying we did this thing with Morava K theories. Morava K theories are not geometric; they're just this algebraic stuff extracted from complex cobordism. But actually, if we had wanted, we would have sat down and written the whole paper. Where instead, throughout the paper, we would have used complex K theory. Why did we not do this? Well, we did not do this because the application to symplectic topology is not as strong. Okay? If you want to estimate the number of fixed points of a Hamiltonian diffeomorphism, and you had done this with complex K theory, what you would have concluded is that it's bigger than or equal to the rank of a complex K theory. And that rank is sometimes smaller than the rank of ordinary cohomology because of differentials in the Atiyah-Herzog spectral sequence. Okay? So that is the reason we didn't do it. But if we had done it, okay, then KU is a very, very nice ring. Okay, this is a nice commutative ring. You can study algebraic geometry over KU. Okay, now a further extension of what we did would be to do not just the Hamiltonian theory. Let's do the Lagrangian theory. So if you do the Lagrangian theory as well, then you can study now Foucault categories with respect to coefficients in KU. But this to me is extremely puzzling because it says that, for example, in the context where we study mirror symmetry, like for example, when X is a K3 surface, okay, usually we study mirror symmetry by saying, okay, we're going to look at this K3 surface and we're going to look at it in characteristic 0, and we're going to match up the mirror in a certain way and have this kind of mirror transformation. Of course, I understand the K3 surface is a very delicate place to make to make these statements. But what I want to say is that this construction is completely canonical. To any closed symplectic manifold, there is a canonical construction of a Foucault category with coefficients in KU. Okay, so therefore you would expect that under the mirror, which is in general, we only think about it in characteristic 0, lifts to KU. Okay, I'm not sure I'm exactly saying the right words, but I think I'm saying something not too far from the right words. Okay, so there should be a way, for example, to talk about mirror symmetry for K3 surfaces, which should be kind of the simplest place where this will become very interesting, where instead of doing what people have tried to do and maybe try to think about like arithmetic mirror symmetry, where you kind of work over the integers, whatever, that somehow, that's like the idea that you can map from Z to Q. And I'm saying, it seems symplectic topology suggests that it's actually much more natural to go from complex K theory to Q via churn, the churn character. And that all the objects that arise in the mirror context have this lift. Okay. So what I don't know enough of is kind of does this give any specific prediction? Okay. And that I don't know. I don't have any specific predictions out of this. But also, I haven't tried yet to understand how this perspective, which will then involve, as I say, Fukaya categories and spectrally enriched Fukaya categories, will interact with the enumerative work that's being done with quantum K theory and so on and so forth. I mean, I think the theories are basically going to be related. Of course, quantum K theory is most often studied and known to be most rich in the context, in equivariant context. And I'm not about to define the equivariant Fukaya category over Ku. That's for another generation. But anyway, I just want to point out specifically for mirror symmetry that there is this now, essentially canonical lift of Fukaya categories. Again, nothing is written yet, but hopefully it won't take too long. Canonical lift of Fukaya categories, and hence, that raises a question for the mirror as well. So, okay, I will stop here.
Thank you very much. Very, very interesting, inspiring talk. Actually, as for the last, very, very last part, I'm a bit confused because basically you are talking about some way of defining the virtual class, whatever, chain using the spectra, and basically like on the moduli spaces you have Buddhisms and blah blah blah. But normally the mirror symmetry, it's not a statement about the moduli spaces on the Fukaya side like this. Yeah, how to see the other B side, the role of the spectra on the B side. What
okay, so maybe what I can say is the following. Maybe that won't be so helpful. So here's something which I totally do not know how to do. But if you run the classical mirror symmetry like the physicists did, then what they would tell you is that there's some correspondence between quantum Gromov-Witten invariants. Well, quantum product, the first one, this Yukawa coupling, quantum product versus period computations, right? Okay, so now the quantum product is some count of some elements of some moduli space of degree 0. This is count of moduli spaces M bar Gn with of X with some count. Okay, so now I'm saying, well, not only can you count them, you can also try to remember their Buddhism class. Okay? Now that's hard because they are stacks and they're derived stacks, and that's just too hard. But what you can do, complex K theory is extremely well behaved and behaves very well for stacks and for derived stacks. Everything is fine. So you can still make sense of the churn character. Okay, so you can make sense, and this is quantum K theory. Instead of your product just being numbers, the way we normally say this, because we like to be, people like to work rationally. So rationally, you would say instead of getting numbers, you get these kind of polynomial, Laurent polynomials. Okay? But in reality, you get much more because cohomology, K theory, has torsion, can have torsion. Okay? And you get operations that you really cannot describe as just a number associated to a pair. You really have to think of it, because things not dualized. You can't just dualize vector spaces anymore, okay? Because you're working over Z adjoint. You're working over Z adjoint UU inverse, and you have some module over this, which is the cohomology ring, the K theory ring, and now you have some quantum product, an actual deformation of the product of the cup product on K theory that is determined by the count of these moduli spaces, but not as numbers, but as as virtual vector bundles. Okay, so now you could say what makes sense on this end. And I have not tried to extract what the physicists have said, even though I know that there is something. But what I'm saying is that from the point of view of symplectic topology, from homological mirror symmetry, what you say, just like Kontsevich said many years ago when I was still in high school, that this quantum product, it comes from a Fukaya category. And these period integrals, it comes from coherent sheaves. Coherent sheaves of what? Of the mirror space. Okay? And there's some equivalence here. We know, of course, this equivalence is not enough. You need this equivalence with a bunch of extra structure. Okay? But now that this Fukaya category, we can now do the same thing with Ku, and that will give rise to this quantum product. Okay? So what is going to be on this other side? Well, hopefully it has a classical description, which I don't know. Okay, but this classical description, I don't think it can be something just about the complex manifold X, which is the mirror. It should be something finer than this. It should be something, this complex manifold, together with some lifting to this ring spectrum called Ku. Okay, but if you want to do it in the kind of homological world, you would just take coherent sheaves over X check with coefficients in Ku. What it means is that X check is defined over Ku. So let me not do that. Let me do that. Ku. Okay, and then this X that we normally study is just obtained by base change, by kind of specializing from Ku to Q. To Q, and that's anyway. So anyway, that's what I'm speculating about.
You're just taking spec of HH0 of your Fukaya category.
No, I mean no, never. And so spec of HH0 is an accident that works when the Fukaya category, when the manifold that you're working with is mirror to an affine variety, because otherwise the ring is not a spec.
Sure.
Okay.
But
I think
a bunch of them together, yes.
Well, yeah, but somehow the point is that but also that has many issues, which is that if you try to understand, that's easy to say. That allows you pretty easily to say what the mirror should be. But if you want to understand what the mirror functor does, like if you're interested in the Lagrangian and you want to know what it goes to, that's completely hopeless to use that perspective. You really have to work with the Lagrangian world. But indeed, yeah, if I just wanted to say, there is a mirror and I could construct it, this may indeed be the simplest way of constructing it. To just say, we've told you how to do the Hamiltonian Fluir theory. Hamiltonian Fluir theory is basically enough to construct this kind of symplectic cohomology. And you take spec, and you assemble those affine things together. Yes.
Yeah, you can also say, naively, that for conventional mirror symmetry, zero level is identification without even the product of the moduli spaces of deformations of both categories. And deformation theory and characteristic zero, all these Hochschild complexes, L-infinity algebras, is now upgraded to something. If you do it in characteristic P, for example, it will be different. And so it's morally what you are saying.
Yes, but again, what I want to say is that what seems extremely natural from the symplectic point of view is not to try to lift to characteristic P or to the integers, not to try to go to some mixed characteristic setup, but to go to the spectral context.
Yeah, of course, yeah, absolutely.
Wait, why do you say K3s are the simplest example? What about elliptic curves?
The elliptic curves just seem too simple. I could probably do it. I could probably do it.
If you're lifting the mirror family of elliptic curves from something over Q.
Yeah, I think I could just explicitly lift the. I can. Yes, I'm sure I could do the elliptic curve case. So I'm sorry. So K3s are the first case that I don't know how to do.
Maybe it's
I don't know how to
pointing. I think that maybe it's worth pointing out that in the case of elliptic curves, there's a canonical lifting of the Tate curve to the sphere spectrum.
That's exactly what I'm trying to say. I think you can just do it. So that's what you. Yes, thanks, Adil. Yes, I think, yeah. So we basically have this Tate curve. It just lifts. I could check that. The symplectic one agrees. I'm sure the symplectic one agrees. Partly because partly because there's no higher dimensional moduli spaces that actually appear. Right. Remember, the whole point is supposed to be that there's some correction terms from these higher dimensional moduli spaces that contribute some non-trivial stuff in higher homotopy groups of Ku. And they will be there I'm sure. But in the elliptic curve case, they're just not there. So
I see. So what you're still trying to do is lift a formal completion of the large complex structure of Mirror to something of great. Do we know examples where that doesn't lift to Z?
I will defer to the experts.
What is the remark, Arnold?
Okay, so what we're trying to study is the formal moduli space around the large complex structure limit of some family of Claviaus. And what we're interested in is making the base as small as possible. So maybe it was previously Q, now we're trying to make it Ku or Fp or Z or S. My question is, do we know examples of large complex points, maximal unipotent monodromy points in the moduli of Claviaus where that family is not defined over Z?
It must be possible. That's all I will say.
Counterexamples, you think?
I to find counterexamples, yes, I think somehow. Again, I'll ask the experts around it. Because I expect that if your Hodge theory near the maximal monodromy looks any sufficiently complicated, you'll start seeing some roots of unity appear.
It's like analogs of elliptic curves with complex multiplication with a bigger endomorphism group.
Right, but the problem is that the complex curves with complex multiplication are nowhere near the maximal.
Yes, they sit inside.
They sit inside. So you need something a little bit more complicated. So anyway, I don't have an example in mind. I would be, but I will, as I said, not claim anything as a result. All I will say is that symplectically, this is not the natural. Now we have a natural statement that these always lift. These always have Ku lifts.
I mean, it sounds like you're also conjecturing K of N lifts.
Well, K of N is a bad ring. K of N is a bad ring. It's not E infinity. It's not E infinity. It's not even E2. It's a bad ring. You don't want. I mean, I can tell you, we're conjecturing the existence of Morava E theory lifts or something like that. Sure. But who cares? I mean, like the real thing you care about, K theory is a nice theory.
Yeah, but it's just the first step, and it seems clear that you're only conjecturing that because we have a nice description of that first step.
No. What I'm saying, we could have redone the work that we did, which was use Morovocating theories. You could basically throw it out the window and do it all instead for just Ku.
Yeah, okay, but like I don't believe that your conjecture is only for Ku.
Oh no. And as I said, I think that the way you conjecture it to a homotopy theorist is to say there are these Morava E theories En.
Right.
And there's a lift to En for every N.
Right.
And really, I think that there is some kind of transchromatic object for which this makes sense, but that's further away.
Right. Yeah. So I was asking a very naive question, like, do we know examples where it just does not lift to Z? And that's there's natural obstructions.
Yes.
Okay, but I'm also confused where you need K of N as opposed to anything else. So there are two obstructions that you raise. One is just ambidexterity to deal with the orbifoldiness in the first place, fine. And then there's this derived stuff. And as far as I understood, so let's separate those two issues. Let's suppose you had some moduli space that has some derived structure, but everything is still built out of manifolds as opposed to orbifolds, together with zero sections of vector bundles.
No, then there's nothing to do there.
Okay, so in that situation, you can work fine with like Z coefficients. That's fine.
Yes.
Okay, yes. So so the ambidexterity is still just for the orbifold. All right.
Yeah. So again, the problem that I want to say is that if your thing was just an orbifold and there was no vector bundle on it, you wouldn't have a problem. If your thing was a manifold with a vector bundle, you wouldn't have a problem. But you wouldn't have a problem means you can work over Z. That's what I mean. But if your thing is a orbifold with a vector bundle on it, then it's hard. Then the difficulties arise.
And all this, I don't know if this is part of the whole like political debate in symplectic geometry or something, but these Kuranishi structures as opposed to like whatever John Pardon did versus anything else, should I think of your definition of your category of charts is just formalizing all of that and just putting it into one big pile, saying you can kick things.
No, I think the short way to say this is that our approach is closest in spirit to Pardon's. For some reason, let me just say, the short word is like, Pardon also assembles the local pieces to the global pieces. Our local pieces look like his local pieces, but he assembles it. The easiest thing I can say is he assembles it via correspondences. Okay. And it's really hard to formalize stuff. And we, kind of do a little bit more work on the geometry side to turn every correspondence into a pair of maps and to add the correspondence as one of our objects in some sense. And then it just makes everything kind of clearer formally.
Okay, gotcha. Do you expect to be able to recover what Paul Seidel is doing with quantum Steenrod, like in some limit of your quantum chromophytin invariance with KFN coefficients?
I haven't thought about it. Maybe I should just say I haven't thought about it. Yes, I think there's going to be some quantum atoms operations and blah, 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 but I have not thought about how to recover, quantum Steenrod operations from this business. That maybe that's all I will say. Because indeed, it makes a lot of sense because Paul's predictions, involve some, strange predictions for, the reduction of some Gromov-Witten counts mod P, which in particular force those Gromov-Witten counts to have been integral, so you can reduce the mod P. Whereas, if you try to apply this, you would get instead something, valued in K theory, and then you could try to reduce that mod P. But anyway, I have not put any thought into it.
Okay, more questions?
Yeah, so what about the quantum covariism? So could you not just do all this with MU as well?
Well, I wish I could. The problem with MU is, the moduli spaces of holomorphic curves don't have fundamental classes in MU. So you could, I have a conjecture. My conjecture is that if you look at so let me first make an easier conjecture, which I'm pretty sure I know how to prove, which is to look at the cobordism ring of complex orbifolds. Okay. That has an inclusion of cobordism ring of complex manifolds. And the statement, again, this is still a conjecture, but this conjecture that feels, you could do, is that this map is split injective. Okay? So there's a retraction that you can go, that you can map the other way, and the composite is the identity. So, fine. Now the question, so let me not say this as a conjecture, the question is the same thing true with the cobordism ring of Kurenishi spaces, almost complex Kurenishi spaces, or if you want, is the same thing through the cobordism ring of derived almost complex manifolds, derived almost complex orbifolds. And, that would be fantastic. And if we did it, then we would be able to kind of do what you asked me, which is to construct this quantum cohomology ring with coefficients and cobordism. This is something that one can start checking, at least checking abstractions to. The global description. When I said that we have global Kurenishi charts, I mean this is fantastic news because this means that we will be able to that you can just appeal to homotopy theory and construct a space, something constructed from Grassmannians, from equivariant Grassmannians, whose homotopy groups will be, and in some appropriate limit, the homotopy groups, the cobordism groups of what did I say, derived complex orbifolds, of Kurenishi spaces. So now you can start computing those things, and you can see whether the inclusion of the usual cobordism ring happens to be split or not. And there's a very good chance that it will be split. At least at the level of homotopy groups, because somehow you're probably just adding even. I mean, now I'm just speculating. You're adding only even cells, and anyway, maybe you're not introducing too many differentials. So that's the kind of direction which I think could answer the question. Would eventually allow us to know whether there is an MU object that refines all this stuff.
Sorry,
That's
very roughly, your split retraction before all the derived stuff just sends point mod G to point from a constant.
right. That is exactly my retraction. Yes.
Okay, very good.
Yes. Yes. So in the orbifold case, you can just do this. And of course, you have to worry because I did a point mod G. Now, what if I take a manifold with some singularities? But if you have a manifold with some singularities, you can run resolution of singularities at characteristic 0. Well, you can't because it's a manifold, not algebraic variety. But in the normal direction, everything is linear. So you know, if you understand, and this is why I'm saying this is a conjecture. I mean, I haven't sat down and proved that you can do this. You know, if resolution of singularities is sufficiently canonical, which I am told that it is quite canonical, then you can dream at least of doing this. Okay, but it's not going to be helpful for our purpose because we want. I mean, it'll be helpful. It'll have some uses in symplectic topology. But if you really want all symplectic manifolds, you want to do this in the derived world, and I just haven't managed to see any geometric thing to that kind of, you know, incorporates this resolution of singularities together with the vector bundles. And so my current idea is that what somebody should do, and one should do is at least try to compute obstructions, try to see whether there's any hope that this is true or not.
I think this story is early days, but I thought Hiro Tanaka and Jacob Lurie were trying to lift the Fukaya category over the sphere spectrum.
Yeah, I mean, they're trying to, so they're trying to give a definition for how you would define something like the Fukaya category, given an input that is something like what symplectic topology gives you. But it won't work because to lift it over the sphere spectrum, you have to assume that your moduli spaces are framed manifolds. So that's what they're kind of doing. Assume that somebody gives you some framed manifolds that are assembled. That are assembled in the way that the moduli spaces of holomorphic curves would be assembled if they were framed. Then under that context, they want to define some category. They would extract from that a category. I mean, I haven't talked to Jacob about it, but I talked to Hiro, and I'm pretty sure that's what they're trying to do. So, if you do that, that's great. But then you actually need to produce it in symplectic topology. And as I'm saying, outside any sufficiently complicated examples, you're not going to get manifolds. And they're not going to be framed, but they can take care of that. I mean, their approach, will be oriented with respect to any, compatibly oriented with respect to any Chromology theory. Then they'll build a category which is over modules of that category, over that ring. But again, in practice, that's not what we get. We don't have manifolds. We have these Konishi spaces.
More questions? Okay, looks like 10 more seconds. Last chance to ask Mohammed. Okay, if not, well, Mohammed, thank you very much for your very exciting talk. And I ask you to email me final version of your notes with these last pages.
Yep.
Okay. Thank you.
Thanks for the invitation.
Thank you.
Bye.